Thank you everyone for joining us. Good morning, good afternoon to everyone, and welcome to the third talk of the EDT Community Seminar Series. Today we are very happy to host another exciting talk given by Guy de Spiegeleer, who holds a PhD in numerical analysis. Guy is a senior engineering in aeronautics, and he notably worked on the design of a cryogenic pump for Ariane 6. He also worked at Safran to prepare the LEAP engine development and later its extensions. So arguably it's one of the most used engine in the world as it is equipped in the Airbus A320 and Boeing 737. He's also co-founder of the Composite initiative, a new collaborative design platform for complex software simulations. And today he will be talking to us about the benefits and an extended digital twin to support design of a complex system. So Guy, many thanks again for accepting our invitation, and the floor is yours if you can share your slides and you can start. I will just stop sharing mine.
Thank you, Jamel. So thank you for the possibility for me to share this work. So thank you all. So I'm going to talk about the digital twin. This work were made. It's based on a study I performed the last couple of years at Safran, especially dealing with system engineering approach. So it's based on the lectures I had from Sesame process at Safran. But anyway, it's a presentation I made by myself. It's not a Safran presentation, actually. So just I will talk about complex systems. So what is a complex system based on what Safran is doing? The aircraft is a complex system, but there are also, as subsystem of an aircraft, some complex systems themselves. For instance, the engine is itself a complex system, and you can go further and see that even inside an engine, this part, it's called the fan blade. It's also a complex system. We'll come back later on it, but complex system is, the complexity can come from many different points. And it's not only something made of several components like an aircraft. It can also be something made of different materials and with different requirements, and that's made complexity. So today, what I'd like to share with you first is that digital twin is great. So that's really for me a revolution, and we are just at the beginning of this revolution. So I will share some thought about this. Second point, digitalization will drastically change the physical system design process, and not only the process, it will drastically change the way I think the designers will work together, the engineers will work together to collaborate and design a complex system like an engine, but not only an engine. It will drastically modify far more than just aeronautics. And last things, software design is an inspiration for physical system design process. By software design, I mean what most of you probably coming from the software development know as a Git, for instance. This is something that drastically changes the way you design your software. And this is something that as a mechanical engineer, I should consider to think about how we could drastically change the way we design the physical systems. So there are inspiration, but as I mentioned, it's not that easy to transpose because there are some specificity for the physical design that are different from the software design process. Just to come back on my experience, so Jamel, you mentioned that, but I will summarize. So I contribute to rocket engine design, Ariane 6, 5 and 6. The design I made in the late 90s, designing the new hydrogen turbopump of the Vinci engine will fly end of this year, beginning of next year. It shows that in the rocket industry, the lead time for design is very long. I was also involved in aircraft, as you mentioned, to develop the LEAP, but also to think about the new architecture that we could consider when we started to think about the LEAP. We first started to think about different architectures that we could consider to change the way we design the aircraft and the engines themselves. So I was project leader for different technologies and architecture that were studied at that time. It was in the year 2005 to 2010. And I was also involved in change project management. That's very interesting. It's not technical project, and it shows that when you introduce some process technology, the way you work, you really have to take care to take into account the people themselves, their knowledge, the way they work. And you cannot introduce new tools or new process like this just by pushing them. So you really have to take care when there is a revolution like we are considering today in the digitalization, that it's not only a technical subject, it's also and probably even mainly a human project or human revolution. So you have to take care of that. I was leader of a design team, designing what we call the fan module. This is the upper part of the engine. And I also made some system engineering with the Sesame approach. And for the last 2 to 3 years, I was leader of a research team at what we call Safran Tech. This is a research group, research division inside Safran that is dealing with research for all the company inside Safran. So there I was leading a team, research team in this complex system simulation and system engineering, and both together. And that during that activity that I was especially connected within Ria and Benoit and diverse team. Just to come back, what is a complex system? It comes from different points. A complex system may be complex because there are different functions. So here is a rocket. It's not only a rocket, it's also a booster that can land. So it's not anymore only something that push when you take off a rocket. It's also additional functions that you have to consider to land it, but also to reconfigure it and to travel it back to the new assembly facility and to relaunch it. So we see that there are additional functions when we consider that the reusability of these rockets. Complexity is also assembly of different components, so that's obvious, but it's also the assembly of different jobs. When you consider a new hybrid engines, you have to consider jobs that were not involved before in your activity. For instance, considering hybridation of aircraft, you have to consider electrical engines that were not very involved before. It's also a question of environment. By environment, I mean connection with the environment. So when you've got a car that is plugged to electrical facility, it's not anymore an isolated car, it's a car within a complex system itself. We can say the same with a drone. When you fly a drone in a city, you have to consider not only the drone flying, but also the buildings, the people, the other drones, and it introduced complexity. Also partners, when you consider a complex system, you are not alone to design it. It's not designed or manufactured by a single company, so you need to introduce some partners, some subcontractors, so it introduces also some complexity. And of course, with considering now life cycle and eco-design, you even have to consider, when you start the design of a new system, you have to consider its life cycle up to the end of the program itself, to optimize the recycling of material and ecological impact. So complexity is anywhere, and it increased drastically with the new project and new product we have to consider today. Okay, so let's come back to an aircraft. So this is just a cross section of an aircraft engine that is used for the Boeing 777. It's a G19. It's made by G and Safran. It's for Boeing. So we see the different partners that have to talk together. It's made of different components. It's obvious, but it's made also of different physics. Here you have the combustion chamber is very, very hot. Here you have the fan module. It's cold. You have got low pressure air coming from outside. You've got a high pressure air going out from the high pressure compressor. So a lot of different physics, dynamics, acoustics inside this system. But you also have to consider the control system with all the parts that are moving. And you also have to consider the trajectory. And of course, you do not design or optimize the aircraft the same way when you consider cruise or takeoff or landing approach. So you have to consider all these phases to design it. So it's also optimized because of weight constraints. So it's really complexity coming from all this contribution. And let's come back to the specific part, the fan blade. So the fan blade is a blade that is inside the engine that you see from above the engine. So it's made for the LEAP. We made it with composite, with leading edge made of titanium compared to the previous technology that was full titanium. So why it's a complex system? Just because you have to consider lots of physics, aerodynamics, of course. This is the shape of the blade that must be optimized to create the thrust. It's also the acoustic. You have to limit the acoustic and the noise generated by the blade. That's the first contributors of the noise. The material, it has to support speed rotation. It also had to support the impact of external objects coming from above and be robust enough to support these damages with mechanics evaluation. FOD, this is a foreigner object damage. Safety, an engine, you cannot accept to make it fail. So if something really important happens, you must be able at any moment to stop it. So it means that you have to contain any external damage. You cannot accept that any object will go out from the engine to impact, let's say, the wing of the fuselage. This is absolutely forbidden. So this is safety is critical in this engine. Manufacturing, of course, you have to take into account manufacturing constraint for feasibility, but for cost as well. Erosion, because you can use this engine and this blade in Arabic with sands, or in Finland with snow, and this external air will introduce erosion on the leading edge. So to support life cycle of the or duration of the blade, you have to anticipate this erosion. Maintenance, of course, you have to change it if needed. And health monitoring, you have to anticipate the modification or maintenance of the blade if something happens. and other things. So you see that just to design this blade, you have to consider at least these jobs, this expertise. So I will not go in the detail of these pictures, just to mention that even this a material like this, it's the geometry, the shape of the blade, it's not unique. There is a blade that you manufactured, but when it's used, when it's in rotation, the geometry, the shape itself, it's modified. It's what we call hot blade, and it depends on the speed rotation, on the pressure field. So this is also the complexity of the geometry itself, and that you have to consider when you evaluate the performance. So very, very important complexity. I just want to come back to something important, I think, to understand that there is a big difference in designing a part and simulating a part. By simulating, I mean, you've got a definition, a geometry, you've got a mission, like a flight or takeoff for an aircraft, and you want to evaluate the behavior of your material, like the pressure field, like the temperature, like acoustics. This is simulation. So you have the definition, you have the mission, and you compute the behavior. So behavior is like a function of design on missions. When you design it, it's different. You've got a definition, you've got a mission, sorry, you want to target a behavior. I don't want my engine to have a temperature over this limit of the material. So this is an input, and you want to evaluate or to compute the definition based on that. So it's more or less a reverse function. So you have to reverse the function f compared to the design part, and you compute, let's say, design definition equal function of behavior and mission. And what is tricky here, if you remember your university or your training, it's not obvious to invert functions. The simulation always exists in this case, because we know that we live in a world where there is only in real life one behavior of an object under mission. So it's just that you will never see two engines splitted in the real world because they are different solutions. So the solution always exists in the real life. So if you are not able to simulate it, it means that your model of simulation is not as a problem. It can be a problem of, it can be a bug, it can be a problem of physics that you do not consider. It's any things, but at the moment, you know that you have something missing in your problem. The problem itself, there is a single solution, and the solution always exists when you do a simulation. When you do a design, it's not the case. Why? Because if you are different designers that introduce different constraints, it happens that there is no solution. And actually, most of the case, if you do not take care, you will have no solution to your design process. Let's consider, for instance, someone from mechanics that want to increase the thickness of a part, and someone from acoustics that want to decrease the thickness of a part. It's not possible to increase and decrease together, so no solution. So when we are doing design, where you design a system, and especially complex system, if you do not take care, you have no solution. So it's why we have really to think about a design process to invert this simulation function and keep the control of this mathematical model. So this is what we call the design process, and we, of course, need tools to design. So let's come back to a general view to the design process. So to design a complex system like an engine, it's to decide of thousands of geometrical parameters, dimensions of all the parts that compose the system. So these parameters, you have to consider the needs and the requirements of your system. You must respect the feasibility and the knowledge of the people that will manufacture and design and manufacture it. And you want to maximize the value of the system you design or minimize the cost. So that's what we could call the design process. So just to illustrate this process, I will write here just one of parameters among these thousands of parameters and a cost function. That's the opposite of the value functions. And you've got here somewhere a place where it's not feasible or it does not respect the requirement, and somewhere there are some points where it respects feasibility and needs and requirements. And of course, you do not know the shape of these feasible parts. And the design process, what is the target? The target is to find here the optimized design. So this is the one that is feasible, that respects the needs and the requirements, and that has a minimum cost. And of course, the question here now is how to find it, because you don't know where it is. So you will introduce some iterative process. The first things you will do is you will start from an existing or something that looks like what you expect to design, so reference. Probably it will not respect feasibility or requirements. So first step of your design process is to study the feasibility of your system. So you evaluate the parameters so that it's feasible and respect needs and requirements. No interest to study something that is not in line with what you want to do. Then your target is to find here the area where there is a target. The problem, or you have an issue if you stay within this part with this limited this frontier here with this feasibility part, because you will never reach after the optimum part. You need to find the architecture of your system that is the most promising compared to the value you want to target. So this is what we call architectural exploration. When you are confident that you reach a good area, then you introduce some improvements. So there are several ways to improve. You can change parameters, change value. You can do many things. It's a continuous process. And of course, you also introduce some new parameters. You increase the representativity of your system. You involve new specialists. For instance, you involve someone from acoustics. Say, okay, here is a system I consider. Is it good for you? And use its own tools and discover that it does not respect the acoustic requirements. So up, you come back to the architectural exploration. So you have this iteration process that you repeat several times. And just at the end, you introduce the last optimization. So that's where you get the additional fraction of value so that you reach the optimum. This part is really important in terms of workload. This is probably on aeronautics where we spend, let's say, 80–90% of the workload, because if you are here, you have no part of the market. With the last 2 to 3% of efficiency, you have most of the market. So that's where the competition is. So in companies like Airbus, Boeing, Safran, Pratt & Whitney, and so on, most of the people are dealing with this optimization. This is extremely important, and it uses huge amounts of data, computation, the CPU, and so on. This is where you put the maximum of effort, because this is an industry that is quite the architecture is the same. Let's say when you look at an aircraft today compared to an aircraft 30 to 40 years ago, they are really similar. So that's an area where there are no significant architecture evolution. But of course, if you are in a new market where nobody really knows where this part, then you need to do mainly this kind of study with architecture exploration. So what I want to mention here is really to be clear, when you do when you design a system, you need to understand where you are in terms of maturity of your market. If you are in a major market, you need probably to involve really accurate tools and large capability of computation because you are in this area. When you are in a not major market, you drastically need modularity and capability to explore a new concept. So that's really different. It's different process, it's different tools. Okay, so let's just go to a next step. And now I consider not only one parameters, but two parameters. This is exactly the same graph than before. This time the target is at the center of the graph. And I introduced this iteration process to understand how I can go to this target. So we mentioned a reference, I call a baseline here. So I've got someone that defined the reference of the product we study. It's most of the case the geometry, let's say reference geometry that is defined by the department in charge of this digital mockup. And this baseline is provided to the different specialists. So I give it to them, and each one asks them to evaluate the performance and the characteristics of this baseline and provide some recommendation to improve it. So someone is considering its point of view, want to go in that direction, another one in this one, this one, and it's normal because each one is looking at the system with its own point of view and with a different specialty. It's not obvious that each one is targeting the same direction. Remember what I mentioned regarding aerodynamics and mechanics, you increase or decrease the thickness. So with this, I've got someone, probably an architect, that is taking into account this recommendation and create a new update, a new reference, a new geometry or new digital mockup, and is providing this again to the specialist. So I do it another time and I iterate this way. And I hope at the end to reach something really near to this target. In real life, like in an aircraft or in a big system like this, one iteration can last quite long. It can be 3 months, something like this. It's long iteration. Of course, we have sub-iteration, but the overall, the main iteration, maybe something like 3 months. And you probably have between 9 months and 1 year to make this design. So it means that you do 3 iterations to 4 iterations, something like this. This is the order of magnitude. So you are probably not exactly there. You are close to, but not there. That's interesting. It shows that the current process probably not converge. And why? Because the efficiency of this iteration process is quite low. And it's especially low when you consider innovative system where you have the risk to have people that provide you with direction that are drastically different. And that's an issue for innovative design. So I will do something that is probably a bit not very rigorous. I will perform the mathematical analysis of this design process. For that, I introduce data. Data is the definition of my system. And I've got the definition at the iteration n. And with this process, I create the design at iteration n+1. So this is just I call a suite. And what you want to find, this is a limit of this suite. And what is interesting, just doing the approximation of this suite, I've got something like this. And this is, of course, not rigorous mathematically, but it gives some very interesting knowledge of what we're currently doing. Data n, this is what you've got at the end of your design process. Data infinite, this is the target you would like to reach. And rho, this is the coefficient here that represents the evolution of your data. Looking at this data 0, this is the initial baseline of your design process. Interesting is to see how you can improve this design process. You can improve it by initial design, the data initial, better pre-design. We know it, if this initial data is close to the final one, you have better convergence of your function. You can also increase the number of iterations you performed. So for doing that, you have to automatize the workflow, the connection between these tools to reduce the lead time of all these studies. So this is automatization workflow, speed of computation, or train people. You can be agile also. But what is far more interesting in this case, can also see how to reduce this value rho. Of course, if you reduce it, you increase the conversions of your functions. And how do you reduce it? But just look at this graph. What means rho? It means that when you are here and that you want to find the direction to the target, and you've got people that recommend some opposite direction, it's difficult to decide what is a good direction. So to improve the design process, just ask these guys to connect their work and give you back a single arrow. So ask them to agree on their recommendation. Okay, so to reduce rho, to improve the design process, you have to introduce some collaboration in this between these guys. It means co-simulation in between these physics. Okay, so that's an important point. To improve the efficiency, you have to introduce, of the design process, you have to introduce collaboration and co-simulation. And of course, you can do that with two specialties, but you cannot, it's difficult to increase the number of people you want to co-simulate together. And that's where you can introduce the digital twin, because that's where it will give some very interesting added value. So the question here is it possible to find a process, a tool to converge the design, or at least to improve collaboration and co-simulation? And yes, with multi-system, multi-physics, and multi-fidelity simulation, you can introduce a way to improve this design, because you introduce a way to reduce this rho value. And that's what we're gonna show later on. So let's come back to, yes, just this is an extract from a document interesting from CESAF methodology. It's Daniel Krobs. It's interesting because it introduced the importance of functional digital mockup to improve drastically the design process of the complex system. But as he mentioned, functional and discipline integration is a key enabler. The question is, how far are we able to provide this function digital mockup that integrate these physics and systems. So let's come back to digital twin. So I will not go into the detail or discussion of what is a digital twin. There are a lot of different definitions. It's not the purpose ici. Here, I will just focus on one definition we had at Safran. This is quite general definition, probably larger than the one, the historical one. This is a representation of a system resulting from the collection of data, models, and information from different points in the system life cycle. So it's really introduced the life cycle and the data and the model all together, and you put them together. So what is a digital twin based on this definition? So it's a digital mockup. This is a geometry. It's also high fidelity tools that you connect to the geometry to evaluate their behavior. This is also low fidelity tools, probably systems tools and monophysics systems tools like dynamic behavior or performance or acoustics. This is also the model to use to evaluate the architecture, so what we call the general MBSE, model-based system engineering, model of architecture. This is also the safety, the list of safety of failures, of course, a cockpit to interact with these tools, some data management to store all the data used in these tools, and also all the tools I forgot to mention. And all these tools are connected. And today, more or less, this is a digital twin. And the key point here is that there are lots of interfaces, connections, and the consistency in the data is not secured. And if you modify something anywhere, how far are you sure that the modification is provided to the other tools that are inside the digital twin? So this is why we introduced what we call a digital twin extension. This is a new device that will connect the different components of the digital twin to secure their consistency, what we call digital twin extended. Okay, but what is it or how it works? So I will just show you and share with you a visualization of an extended digital twin for an aircraft. So an aircraft, it's made of, it's a system, complex system made of subsystems like the wings, the landing gears, the engines, all connected. The aircraft is in the sky, of course. It's very important when you consider a system to consider its environment. Some components of the aircraft are also complex systems. So like the engines, they've got compressor, combustion chamber, turbine, shaft. Okay, so this is the what we call the product breakdown structure of your system. And now you're going to introduce some physics. The first physics you could introduce here is the geometry. So you can introduce it at different levels. The geometry of the sky, this is the position of the ground. The geometry of the landing gear, in this case, this is a definition like the CAD file of the landing gear. The geometry of the aircraft, this is the position of the subsystem together, the relative position. So you see that there are different point of view of a single physics. Geometry of engine, this is position also of the subsystem. Now I will introduce, using same way, a new physics like the aerodynamics. The aerodynamics of the sky, we call it the atmosphere, depending of the altitude of the aircraft. The aerodynamic of the wings, this is what we could call the lift and the drags. The aerodynamic of an engine, this is a thrust. Of a combustion chamber, this is a combustion. So the dynamics itself, aerodynamics, has different definition among the different positions within the system. And I continue this way. I can introduce some other physics like cinematic, dynamics, mechanics, or acoustics, or control, and so on. So this is the extended digital twin. And now let's come back to the connection of this device to the other part of the digital twin, like the digital mockup. So we'll connect it to the different geometrical physics. You can connect the high fidelity tool. For instance, if you compute aerodynamics of the turbine, you connect it here. You connect it also to the geometry. You can connect your low fidelity tools, probably at an intermediate level in your system. And I will not highlight this, but okay, this is what we call the model of behavior on the workflow simulation. This is the device inside the digital twin. You can connect it also to the model of architecture and to the safety assessment, and to the cockpit, and to the data management. So you see that with this kind of device, you can reconnect naturally all the part of your digital twin within your system. So this system, it's a model of behavior of your complex system. It is itself a complex system that you have to consider and design using the process of the complex system. So that's what we did, and here is an example. It highlights a proof of concept that we developed at Safran. It's called COSAP. It's available in open source today. Not this model, but the kernel of the tool is available, and we'll just highlight some of the elements we did with this tool. So it's a real-time video. This is an aircraft. It's a LEAP-1A from Airbus A320. The geometrical view. This is a system view with a system made of subsystems. The engine made of low-pressure turbine made of different stages. This is evaluation of performance of the engine. It's the consumption. And these are the inputs. The inputs from the specialists are of different kind. You can have the specification, what is the trust expected from the customer to design this engine. It can be also a capability, what is the limit, the maximum temperature you can address with the material you have in the combustion chamber, or it can be just a design parameter that you have to select to minimize the cost function. And that's what I will highlight here. Is the parameters here, it's a low pressure ratio. It's the pressure ratio of this fan blade. And if you change it, you have to increase or decrease the diameter of the engine to respect your thrust. So you will see in this video that when you will change it, the value, you will have the modification of the geometry, and here on the modification of the performance. We repeat it, so just we change it again. So look at here the geometry and the performance. Okay, so in real life, in real time, you've got the impact on the geometry and the performance of the modification of these design parameters. So that's what we did now 2-3 years ago, and it proved that when you make the assembly of different physics, like the geometry and the performance, with a good way, you can make a tool that is nearly interactive to the designer. And you can imagine, we imagine some extension here, just an extension when we introduce some discrepancy in the different parameters inside the engines, because when you design it, you are never really sure that you master perfectly the performance of your components. And so you introduce this discrepancy, and you generate by simulation 2,000 engines going out from manufacturing process, and you evaluate the performance view from the customer. What want the customer in an engine? I will just stop here. When you deliver an engine to a airframer like Airbus or Boeing, what they want to know is what is a potential life duration of the engine. And it's identified by the temperature you have to put in the combustion chamber to respect the thrust that is necessary to take off. So you to adjust the thrust, you have to put additional fuel in the combustion chamber. So it increases the temperature of the combustion chamber. And of course, when your engine is getting old, the efficiency is going down. So you need to put additional fuel to make it to respect the thrust. So it increases the temperature. It's what we call the EDT margin. So this is what the customer wants to know. Temperature at the turbine. So it is now evaluating the 2,000 engines. Okay, so it's always real life again. So here you have the 2,000 engines that are integrating. Okay, stop here. So what you see is this is the temperature of your engine, and this is the number of samples you manufacture, and this is a design value you impose for when you design your engines, and this is the discrepancy of your real performance. Considering the discrepancy in the performances. So what is interesting for your customer is not this value, but this is this one where 80% of the engines are below this value. So this represents your performance in terms of manufacturing and the value for the customer. So what we see here is that few minutes after you made this design, with this kind of tool, you are able to evaluate a new value, an additional value that usually you have several months after the time you started your design. And it's because you were able to connect these different physics in this extended digital tool. I will not go into the other elements, but they are similar. Okay. I think that I'm going out of time, so I will go out of these things just to let time. Well, okay. To conclude, sorry, I took a little more time than I thought. As a conclusion, well, digitalization will drastically change the physical system design process, and not only the process. With the kind of tool I just mentioned before, the work performed by the designers will be different, as they will not work anymore isolated from inputs, taking inputs and providing outputs. They will have to work together in real time. For people involved in the software development, it's similar to what is introduced with the Git, where now today, when you develop a software, all the people are more or less working together on using a Forge or a GitLab, GitHub. The methods and tools have just started their transformation. That for sure today, most of the methods that are used to design this complex system are based on thoughts and architecture that were defined in the 80s or 90s. There are new visions that are introduced, but most of the codes remains on a quite old architecture. So we'll drastically change this in the following years. And digital twin extended is great and will be, for me, the key element to drive this transformation. And we prove that it's already possible to perform an extended digital twin. The capability of the soft is available, so it's just a question of decision now to develop and use it for a dedicated design, complex system design. And the question, the Git eng is the idea to really adapt to the design of the complex systems, the knowledge, the process that were used in the for the development of the software. That's the end of my presentation, and here just a team that is that we are currently organizing a team to provide the COSAP to the customer. So under process to create a company with these guys. Okay, so thank you for your attention, and sorry I was a bit longer than expected, but I am open for question if you have. Thank you.